All right, in this video, we'll see how to evaluate compound propositions. We know how to do the basic ones that are built using just one and or one or one not. And now we'll see how to do it for more complex propositions, compound propositions. And that's the goal. We're always trying, we're always aiming for finding truth values of compound propositions. Math lets you build compound propositions of arbitrary complexity. So for example, if PQR are some very simple propositions, then I can just randomly throw things like P or Q and not R, or P and R and not P. Why not? So here's an example of I should put brackets properly. So here's an example of a compound proposition. And that's what makes math so complex and powerful, that you can create these complex structures and you can still understand what they mean by just unraveling the definitions. If you look at this particular example, all it has is lots of ands and ors and nots, and that's it. So we can determine its truth value if you know the truth value of P, Q, and R. And how do we do that? Let's see it. This is too complex. Let me do, for the sake of time, a simpler example. Let's do determine the truth value of P and Q or not R, given that P, let's say, is true, Q is false, and R is also true. So that's the question. Here's the solution. And the solution, for the solution, you have to remember this very useful analogy. It's not a rule, so you don't take it as a theorem, but it's something that helps me to solve these problems. And the analogy is the following. Compound propositions, evaluating compound propositions is like doing arithmetic. It's very similar, as we will see. And what more precisely, if you have the operator not, then you should think of this as changing sign. So not changes true to false and false to true. If you think of this as changing positive to negative and negative to positive, then you can think of and as doing multiplication, and you can think of R as addition. There is a way in which this can be made precise, which we will see in Boolean algebras. But just use this analogy for now to figure out how to proceed. Don't use this as a statement or a theorem. So now let's do the solution for the problem. So I am given that P is true. Actually, let me use colors. I'm given that P is true, Q is false, and R is true. Okay, so this is what I'm given. I should write that. And from this, I want to evaluate P and Q are not R. So first thing I'll do is I'll just plug in the true, false, and true for P, Q, and R respectively. So this will look like true, false, and true. And now let me plug in the other ones. So true and false are not true. Okay, so all I've done is I've plugged in true and false for P, Q, and R. Then now imagine that I was solving this arithmetic problem. Then what I'll start with is changing the sign. And so I will flip the sign here, and this will not change, and this true will become false, and everything else remains the same. So that's what I mean by think of this as being arithmetic. Uh, and when you have brackets, you start with the thing which is in the smallest bracket and then move outward. So that's what I've done here. Now we focus on one of the brackets. So let us focus on true and false. Now, and requires both statements to be true for it to be true. And here one of the statements is false. So this will become false. And I'll just copy the other thing down. And now I have an or, and false or false is still false. And so this gives me false. And I can say that the truth value, I'll just write this here, of P and Q are not R is false. So that's how you evaluate compound propositions. You think of it as arithmetic. You start with the innermost bracket and you slowly expand it out and get the whole expression in the end. Okay. Just do it systematically. If you are systematic, you will not make mistakes. Take your time. Don't skip steps, even if it looks very simple. It's very tempting, for example, to do the knot in your head, but you should make sure to write all the steps separately. So that is how you do truth values of compound propositions. And now we can also use this technique to build truth tables. But let me start with a disclaimer. This is the second part. This part is extremely tedious and it's not really used in real life. If we were to do this for every problem, we will never get anywhere. But we need to know this because this is the foundations of logic. So right now we are building the foundations. We're trying to understand what logic is. That's why we are using truth tables. But you will see that later on you will use other techniques which are much faster than building truth tables. So that's a disclaimer. You will see it's a long process. It takes a long time, but that's okay. You have to do this once in your life. I did it when I learned logic, so now I'm giving it to you. Let's do the same problem, but now I'm not given the truth values of the individual propositions. I'm just given the whole compound propositions, and I want to build all the possible values. So question, or draw the truth table for, let's use the same one, P and Q are not R. All right. So as before, I will start with the individual component propositions. So they are P, Q, and R. But because this is a complicated compound propositions, I will in fact also include P and Q and not R. So if you think about what this proposition is, it is taking the R of P and Q and not R. So I'll think of these also as my component propositions. And finally, I will add P and Q or not R. So these will be the columns of my truth table. So that's 1, 2, 3, 4, 5, 6 columns. It's going to be massive and it's going to be a little painful. All right. So now I want to build this truth table, but before I do that, I need to digress a little about columns. So the goal of our truth table is that you want to find all possible combinations of P, Q, and R. So P can be true, Q can be true, R can be true, or P can be true, Q can be true, R can be false, and so on. So you want to create all the possible combinations without missing any. And there's a systematic way of doing this, which is as follows. So if I have just one variable P, then all it can be is it can be true or it can be false. So I'll just write that here. Now, if I have two component propositions, P and Q, now if P can be true, I'll just tell you the trick. It's easier to show it than to say it. So what I'll do is I will double everything. What I mean is I'll take the T and I'll make it 2 T's, and I'll take the F and I'll make it 2 F's. And then I'll do for Q, true, false, true, and false. So for whatever is there for P in just one variable doubles when you have 2 variables. And the process continues. If you have 3 variables, you again double everything. So now if I have P, Q, and R, initially in the previous case, I had 2 T's and 2 F's. Now I'll have 4 T's and 4 F's. T, 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 F, 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 F. Now for Q, TF, TF, that will become TT, FF, TT, FF. So T, T, F, F, T, T. Oh boy. And then R is just TF, 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 TF. So the last variable is always just alternating T's and F's. And that is how I built my columns. So let me copy this so that I don't have to do this painful process again. I'll paste it here. And again, why are we doing this? Because I want every possible combination of true and false for P, Q, and R to show up somewhere in this table. All right, now we are ready to build. So first I have P and Q. P and Q is just built out of these 2 columns. So I look at these 2 columns, and is true only when both are true. So in this case, that is here, here, and that's about it. So everything else is false, 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 false. Now let's look at the 5th column. Here it's not R. Not R only depends on this. And not R only is going to flip. So wherever there was a true, this will become a false. So false. And whatever was false will become a true. Finally, almost there. Finally, these 2, P and Q, or not R, is built out of the 6th column is built out of the 4th and the 5th. So now I'll focus on those 2. And R is true when either of the 2 things are true. So we need to figure out when that happens. So it happens in the 1st row, 2nd row, 4th, 6th, and 8th, and everything else is false. And that is, you have constructed this enormous truth table for P and Q, or not R. We don't do this in practice, but this is how logic is constructed. This is underlying all of mathematics. Yeah, so that is how you find truth values of compound propositions and build their truth tables.